Okay, welcome to this second lecture on capacitive sensors. So last time we had a introduction to the course, what the course content was, and a little bit introduction to today's lecture, which is capacitive sensor front end. So the outline of this course is that I will repeat a little bit about the capacitive sensors because we have to know a little bit about them. I won't go in depth, but so that we know what kind of properties that are important that to be aware of when we're going to design the front end. And the properties of the front, which are important, as I said, and then I will show you some front end circuits. So if we start with the basic, just look at the two parallel plates which are placed approximately of each other with a given distance d, and they have an area A. Then the capacitance C of these two can be given by this well-known equation, which we start with this C is equal to Q over V, is charge over the voltage. And then we know the voltage is the electric field over the times the distance. And then by using the Gauss's law, we can rewrite this one here and replace the field by Q over epsilon A. Then we get this well-known equation for the capacitor, which is C is equal to epsilon A over D. So we have all the parameters which we need to calculate the value of the capacitor. So A is the area, is the overlapping area of the two plates. D is the distance between them, and epsilon is the permittivity of the material between the two plates. So since we have three parameters, physical parameters, which describe the capacitor, then change in all of these will give us or can be used as a measure of change in a sensor if the capacitor is if these two plates are used as capacitors. So if we change the epsilon by changing the material between the two plates, then we can basically have a capacitor that measures the permittivity of the materials. So such as sensors are being used, I know, in oil industry when the oil is pumped up from the well. Usually is mix of different gases and liquids, such as oil, water, and then it might be some different types of oils. And then by measuring the this permittivity, then they can say something about what the content is. Maybe not detailed, but have an idea how the quality of the oil is, which has been pumped up. And if you change keep the, for example, A and epsilon constant, and you change the D, then you have the D-type capacitor, which is being or sensor, which is being used often in sensors, which is the most common type. And also, if the plates are moving to the sides, then we can then we change the overlapping area, and also we can get the change in the value of C. So many different types of sensors can be made. So capacitors are being used often in sensors, especially in microsensors. This is due to many of the good properties that they possess. So basically, they can allow us to have non-contact measurements. So we don't have to have physical contact with the measurements. So normally they can have simple principle because we have the two plates that I presented, I showed you. Is really well known principle. Capacitive sensors in microsystems are really compatible with CMOS technology. Basically, if you have two plates, if you modify, for example, the two metal layers on top of a chip, then basically you can make a capacitor. Normally they are easier to fabricate because when you fabricate things in micro nano, then you need different processes, which are kind of such as etching, doping, different types of them. I don't want to go into that discussion, but for the capacitor, it's easier. You don't find out the process which is most challenging is the doping process, because you want to make some materials conducting, and then sometimes it is not needed in capacitive method. Depends on how you do it, but again, if you have two metal layers or silicon which is already doped, then you don't need the capacitor. You need the doping to make the capacitor. So you can make them by MEMS, then you can make them in micro sizes. As I said, it can be applied for measurement of several types of physical quantities. The most famous one is the accelerometer. So I think everybody is carrying an accelerometer in their phone, which is based on capacitive measurement. And then they do not require continuous bias current. I will come back to that. Can be unaffected by temperature, because if you have two plates which are at a given distance, then the temperature changes won't affect them as much as, for example, as a resistive sensor, which is basically could be as a temperature sensor, because it's resistive and is really susceptible to changes in temperature. And then capacitors among the electronic devices are the most ideal components in their behavior. So, to summary, pros, they're easy to manufacture, easy to read out. Low power you can have low power front-end circuits, and they are fast. So they are one of the fastest types of sensors that we have. Drawbacks is that since they need to be biased by high voltages, then they might have leakages. And if we make them in micro nano size, then the values are normally really small, which makes the development of the front end a little bit challenging. So in the microsensors, microsystems, we have normally two types of sensors, capacitive sensors. The parallel plate sensor, again, the parallel is a mistake. I forgot to correct it. It should be 1L, but the parallel plate sensors, as I showed you the principle. So normally they are being used often in pressure sensors, where a air pressure normally presses a thin membrane, the top layer, for example, and then this thin membrane is banded in toward the bottom plate, and then you will have a change in capacitance. Or you can have the finger structure or the COM drive, where you have many fingers and you create capacitance between them, and you keep some of the fingers not moving and the other ones moving. The reason that the COM drive has been developed is that the parallel plate principle doesn't give us so big different. So the capacitance changes are small, especially in micro size. And then an alternative way has been developed, which is the COM drive. I will come back to that a little bit. Capacitive sensors, in order to read their response, they need to be biased. So it means that we need to apply voltage across the two plates. There are two types of biasing. Voltage biasing, basically apply voltage across it, is easy. It is the most common way of doing it. And you have the charge biasing. Is it a bit, again, is a bit difficult to make. You need a little bit more complicated circuitry. At least you need current mirrors in the simplest form. And then these two, the voltage biasing and charge biasing, can be a DC or AC. And if they are AC, they can be sine wave or square waves. And again, they have their own challenges. So, and then their drawbacks. So measurement system based on sine wave excitation or biasing can have higher resolution, but meeting requirements of cost, because you need a circuit which produces a sine wave and then reads and then again converts it to the DC values which we are interested in. Power consumption may go up, and the flexibility becomes a little bit different. Again, this depends on the design, but it's a little bit, if you look at the general, so that you can conclude with these things. So if we go back to our power plate, let's say we have the two plates, and then in order to use this one as a sensor, we need to bias it. So we apply voltage across it, and then this will create an electrical energy stored between the two plates, which is given by this well-known formula, which is U is 1/2 CV square. Or if you replace the C with Q over V over, yeah, so this over C. If you replace the Q as this top one here, CV, then we can rewrite this equation as this one here. So kind of we get rid of the V in the expression, because then by this one we can see that by applying a charge we can also create an electrical energy. Yeah. So when we apply this voltage, then there will be force between these two plates. The electrostatic force which will depend the direction of the electrical the voltage will either be the moving plane will move either toward the non-movable plate or away from it. Depends on the polarity. So, and then in systems and sensors, normally we place a spring in between the non-movable plate and the movable plate, and then when we apply the voltage, let's say the voltage has the polarity that these two plates are being pulled toward each other due to the electrical force, then this spring will have or a mechanical force. So the mechanical force across the spring is well known. It's basic physics. It's Kx. K is the spring constant, and the electrical force, we know it from this equation that we know from here that we presented earlier. So when the voltage is applied, this movable plate will move, and then where it stops depends on the equilibrium state, which is kind of the point where the mechanical and the electrical force are equal. So when these two are equal, then we have equilibrium and the plate stops moving. And then if we from these two, if we put them on each side of this equal sign, and then we can find an expression for x, where the distance between two plates is. So let's say we apply this voltage and we increase this voltage. Then this voltage, so when the voltage is increased, the movable plate will move toward the anchored plate. And then at the point, this movable plate will collapse onto this non-movable plate. Then we will have a short circuit. Since the mechanical force is constant, it can be presented by a straight line, and then the electrical force will change dependent on the voltage, and we see that it's a non-linear form. And then we will have for V1, if the voltage is small, then we will have two, according to this equation, we will have two equilibrium points. And then if they increase the voltage at one point, then we will have only one point where these two curves cross each other, and that point is a critical point, because if we go over that, then this plate will move all the way in and collapse. So when we bias the capacitor, the capacitive sensor, in order to make a front end for it, so we need to be behind this critical point, which is the which is referred to as the pull-in voltage. So the voltage that will create this effect that this mover plate collapses is called the pull-in voltage. So we should try to avoid it. As you see, there are two equilibrium points on this line. The reason we have these two is that it's because of these two equations that are equal to each other. So we get two equilibrium points, but actually in real world, one of them is valid. This is the ones that are in this area here. These are not valid. So you will never meet these equilibrium points. If the plate is in this distance, it will just collapse. I don't want to go into that discussion because that's mechanic of this. But the most important thing is that when we bias these capacitive sensors, we should stay in this region from the area which is the pull-in voltage and out. And the pull-in voltage, we can find expression for it. If we have the expression for the voltage here, then the pull-in normally occurs at the distance over 3, and then by putting in this one here, and then we can find the expression for Vp. So how it's found is, again, I don't want to go in this one here, but because that's the mechanical part of it. So COM drives, which are the normal type of capacitive sensors in microstructures, especially when we make accelerometers, are made in this way. We have some fingers which are not movable, and we have a set of fingers which move. So which way they move or how they move depends on how they are anchored. So in this case, to the left is a transverse movement, and if you anchor the movable part like this with springs which are parallel to the fingers, then we get this transverse movement which goes from side to side. And then the capacitance change will be the change of capacitance between each side of the fingers, which can be basically easily calculated if we know the sizes of the fingers. And then if we anchor the movable plate, such as the one in the figure to the right, then we will have a lateral movement. Then the movement will be up and down in this case. And then again, we can find the values for the change in the capacitance. And also we can define the sensitivity as the delta C, the change in the C total over the X for the transverse movement, and the delta Y for the lateral movement. So Y and X is the direction of the movement. So basically. So when, let's say we have this kind of structure, with plates goes up and down, all of these mechanical structures or sensors, capacitive sensors, which are based on movement and have a spring, can be modeled as a spring dashpot, a mass spring dashpot system, where you have the mass, total mass of the system, and you have the spring, which normally is the way we anchor them. They are in that, and then we have a damping part, which is normally due to the air damping and other types of damping in the structure. So it gives us a spring mass dashpot system, which is second order system, which can be found in by this finding the spring constant, the forces. Look at the forces, such as here the And then we have the spring force and the damping force. And then we can basically calculate those to get this second order equation. So the one important parameter from this one here is the resonance frequency of this structure, which is the square root of spring constant over the mass. And the quality factor, which we are interested in, which when we design the sensor. So again, the second order part, I don't go in through it because it's a mechanical part of the structure, and then it's kind of out of scope of this lecture. These kind of structures, they are also kind of have their own noise, which is basically can be modeled by the Brownian motion, which is given by this equation here, which we see that the temperature as an important factor, and also the damping and decay. So for the total noise equivalent in an acceleration, so if it says an accelerometer, then in this structure, we see that it is given by this equation, which is the Brownian noise over the M, and it means that if you want to decrease the noise, then we can increase the M, the mass. Again, this is a mechanical part of it, but as an electronic designer wants to make a good design for such a circuit, maybe it's good to know about these parameters. So capacitors can be designed as sensor, and then they can have different types of movements, different directions, but at the end they can be modeled as a variable capacitor, as a varactor. So the figure in the C, you see that both of these two figures in A and B are being modeled as a variable capacitor. And then the variable capacitor, if the distance is, let's say we start with saying that the change in the capacitor is due to the change in the distance between the plates. And then the capacitance CD can be modeled by this one here. And we normally in microsensors, the change in the capacitor is much smaller than the capacitor size and the initial capacitor size. So the delta D is so it basically is due to the small change in D. So if you assume that delta D is much smaller than D0, then this expression can be approximated as this one here, which says that CD is equal to C0 plus delta C. So then we have a expression for this one here, and then we want to bias the circuit. As I said earlier, we can bias it using a voltage or a charge. So if we apply a voltage charge, we have the voltage biasing. If it's an accelerometer, then basically apply voltage across the two plates, then the biasing is done. But if you want to have a charge biasing, then you need to have some charge current sources, and normally they can use in the simplest form the current mirror. Here's a circuit from a paper called Constant Charge Operation of Capacitor Sensors Based on Switch Current Circuits, and they have created a little bit more complicated current mirrors. So again, there are many works in literature, that can show how it's been done. So what is the difference between voltage and the charge biasing? So as I said, the voltage, so the biasing can have effects on the circuit, on the sensor, I mean. So if we do, So basically, there are two types of nonlinearity in the system due to the one, the electrostatic force, and the other one is due to the structure. So when we bias it, then we kind of introduce a nonlinearity into the system. And again, as I said, if the voltage is too high, then you might get the pull-in. But if you compare the charge biasing and the voltage biasing, if let's say we start with the simplest form, which is a constant biasing. If it is a constant charge biasing, so the offset resulting from the electrostatic force is constant. Because if you look at this equation here at the bottom to the right, then we see the electric force that we have due to the charge biasing. It is not dependent on the changes in the distance. We don't have any parameter at the D is not here. We have Q and epsilon and A. But if you have the voltage biasing, and then we can see the same equation can be rewritten for the voltage, then we see that the distance D comes in, will play a role into the electrical force, which will create a nonlinearity. So the electrical force depends on the distance. And the distance also is the measurement, what we measure is kind of. So it will play. So that's why the charge biasing is, we can say, is constant, and it can be removed by the electrical signal processing. But the voltage biasing will create a nonlinearity into the system. However, the charge biasing is a bit more challenging. It's difficult to have good charge biasing circuits, and then we have leakages in the system, so the charge will not remain, and then it's kind of a bit challenging. So from now on, all the circuits I present, they are based on voltage biasing. So one way to remove the biasing issue is to use a differential types of sensor. So previous when what I showed you was this CD here, which is a single-ended sensor, and this one, if you bias it, it will have a nonlinearity due to this biasing effect. But if you use a differential structure like this one here, where we have the mass, for example, this is an example, which is suspended to the structure here using two springs, and the mass can move up and down due, for example, to some acceleration, and then it is placed into a box where the bottom of it has a conducting layer, and the same thing we have in the top layer. And when the mass goes up and down, then we will have two variable capacitors between under and over the moving mass. So, and this one can be modeled as the figure in B, where we have two variable capacitors. And then these capacitors will increase their size and decrease opposite of each other, which can be modeled as this one here. The change in, you see, when, for example, the mass goes up, then the distance between this capacitor here, D, decreases, and CDP decreases, and CDN increases, and then we'll have change in the capacitance. So this is one way of doing it, and differential capacitors are being used very often. They are the most common ones normally, especially in accelerometers. So in the last lecture, I touched a little bit upon this thing I'm going to present now, is the effect of the electrostatic force on an accelerometer. So if you say that this structure here is an accelerometer, and this one, the movable plate, is in the middle, which is, it experiences force due to the acceleration, and the force is equal to mass times the acceleration. And we need to bias it. We apply voltage across it. And how much biasing should we have? So this is the expression which is for our system. And then, so we have the M is the mass, A is the acceleration, and is equal to the expression for the capacitance changes. If we reorganize this one here and rewrite it such that we get a fifth order polynomial, then we get this expression. And from this one, we can, if we, for example, choose a structure, an accelerometer with these parameters, where we have a mass of 1 milligram, epsilon of 1, K, the spring constant is 5 Newton per meter, and then area of 1 square millimeter, and the distance 0 when the plates are not moving is 5 micrometer. Then, obviously from reference, the reference is missing here. I don't know why, but I will, yeah, it's kind of, but I think I have it in the last slide, I think. So we see that by increasing the voltage, the bias voltage, VV, then we will change the behavior of the accelerometer. So the x-axis is the acceleration, and the y-axis is the change in the distance. If we don't have any biasing, then this system with these parameters will have could have a measure for an acceleration from minus 25 to plus 25 meter square second, can vary between minus 5 to plus 5 micrometer. If we increase the voltage to, for example, 1 volt, then we see that the range decreases. This due to the range due to the acceleration decreases from almost minus 3.5 to plus 3.5 micrometer. And if it's increased to 4 volts, it will decrease until minus 1.5 to plus 1.5. And then also the system becomes a little bit less linear range. The linearity decreases, but it becomes more responsive. You see the curve becomes more sharper. So the biasing will change the properties of an accelerometer. So yeah, this is another curve shows what happens if you increase the biasing for the same structure. I had to jump over one slide because that was the repetition of the previous ones. But we see that the delta D as function of VB. So as VB becomes 6 volt, then the delta D becomes 0. It means that the electrostatic force becomes so strong that it doesn't allow the mass to move anymore. And VB versus acceleration, again, the same thing. So at 6 volt, the acceleration that we can measure is almost 0. Yeah. So again, a little bit of the same. The two biasings, they will have effect on the circuit. So it's important to be aware of this. Yeah. So we go back to our circuit, which is differential sensor. Then how do we bias such a system, which is a differential? We can have a time continuous biasing or continuous time C to V conversion, basically by applying a DC voltage on each node, outer nodes of this capacitor. Here we have a Vref plus or minus Vref, and then we read the voltage in between. So in this case, it's based on the voltage divider principle. So when the capacitors change, then the voltage the in the middle will change, and this can be amplified by an amplifier. The challenge is that if this change of the capacitances are slow, basically it becomes really difficult to measure anything in the middle here. So basically you can say that DC accelerations cannot be measured. So if you have really high frequency vibration in the middle, then we can measure something. We get some changes in the middle. So this type of biasing is not used so often, as you see the reason. That's why I don't want to go into it. Just before we continue, I can show you that we can also bias this circuit in different way. So this one is a single-ended output. It means that we have one output, but we have two biasing. We could also bias this differential capacitive sensor by biasing the node in the middle and have a differential output. Then we can use a differential amplifier to read its response. Again, it's not capable of reading DC acceleration signals. I mean the small variations in C. So one way to deal with this is to having a time varying signal at the input. So here we have a so the time varying can be both sine wave and square wave. Here we have using a square wave for the same circuits that I showed you here. Here's the single-ended output, differential output. Here we have differential single-ended output to the right, to the left, I mean, and then differential to the right. So this one is capable of reading small, slow changes in C. And then we need, at the end, we need a C to V conversion, which basically removes the high frequency at the inputs of the capacitive sensor. So how we can implement them? Basically, the clocks, the pulses can be generated by having switches, which can switch between VDD and ground. Here's an example. I will come back to this one here. This is a delta sigma model of a switch cap. Basically, it has a feedback. You see the output B is kind of fed back to the input and controls kind of the switches which control the clocks. And then due to this feedback, we get a delta sigma modulation of the change in capacitor to the output. But again, I come back to this. It is just to show you how we can implement this change varying in the creating these pulses at the input basically by switches. So here we talked about how to bias them. Normally, we have also other effects which are unwanted. We have when we use electronics, then we have the biasing in the circuit, the self-bias. For example, if we have, normally if you have an ideal amplifier, which means that you have a 0 in, you have 0 out, but normally it's not the case. The amplifier is not ideal, and then they have some unwanted bias. And we have also noise in the system. There are many ways of removing them, but the common ways, some of the common ways are the chopper stabilization technique and the correlated double sampling. here I just had this text, a little bit long text for you if you want to read it, because this lecture doesn't have any book. So I just, from reference one, I took some of the text and put it here. So yeah. So basically, correlated double sampling reduces the low frequency noise by high pass filtering, whereas the chopper stabilization translated into out of band frequency. I will talk about a little bit about these two techniques. So again, a little bit text here for you who want to read it, because I just, again, since we don't have the book, so I just put the text here so it can be more, you can read it yourself. So if you look at the chopper stabilization, it's basically, there are many ways of implementing it. If you look into the literature, different books, different ways of implementing of this technique exist. Here's an example. So as the name says, chopper stabilization. So CHS or CS, as you see here, you CHS, but here's just CS. Basically, what you do is you chop the signal. And then you need, in order to do that, then you need a pulse and some switches. So in this case, here's an example with the auto zeroing. So here you see of a system where it has a sample and then auto zeroing phase. So we see that it has basically two clocks which switch, but at the input and to the output. So when the clocks here are on set, then we are in the auto zero position. What happens is that the input of the amplifier is connected to ground and the output of it is connected to ground. And these C1 and C2 are being charged by the, sorry, C2 and C3 are being charged by the unwanted biases in the circuit. And then as signal, the switch turns over to the S, then the signal path is going through the input to the output. But the unwanted effects, which are the values which are stored on C2 and C3, have been subtracted from the signal. So we get a more kind of ideal signal going through. So again, this is a course about sensor front end, but again, the topic of chopper stabilization, could be a lecture in itself. So I recommend for you who are not familiar with this technique to go and read this. So in my course that I have in Norway, then I use one lecture just to discuss the chopper stabilization and the correlated double sampling technique, because it's important that we have a good understanding of this. But I assume that the persons who take this course have this basic understanding. So here with us, we have this. So either I have this in my course, I talk about it, or if I know the students have it from previously, then I don't go. But this is kind of a prerequisite for this course. This knowledge is not basic, but this kind of knowledge is necessary. So how to implement this? Using switches and capacitors. The correlated double sampling is another method which basically can be designed in this way. Again, it is made of many types of many circuits, transistors and capacitors, and by switching these with a different timings, then we can achieve the double sampling. Basically, the idea is that you have some capacitors in the circuit, and then these capacitors store the unwanted values in one period, and then in the next period, they kind of, by adding or removing these unwanted values from the signal, then we can get a better signal out. So here I have this circuit here. I have to the left, figure 14. Here is for phi1 and phi2. I have tried to explain the two. I'll try to explain it really shortly. So at phi1, if you look at the switches which are on, this phi1 is on. These switches, we see that the signal, the input signal goes through the system, and the system works as basically an amplifier with a capacity feedback. But at phi2, if you look closer into it, then C1 is connected to ground, is discharged, and C2 as the same, but the input is going through through the other clocks through phi2 at the bottom line, and then we'll have an amplification. But at this point, when the switches are this way, then some of the unwanted values are being stored on this capacitor. These are the biases in the circuit by the amplifier. So, and then, so some value is being stored in one clock, and these are stored here and here, and then the next period, these are being subtracted from the signal. Again, it's a little bit difficult for me right now to just try to explain the principle, but the idea is that you, on one period, you store the unwanted values, and the next period, you subtract them from the signal. So you get, so you can remove the different biases in the signal, from the signal in its path going through the front end. So here's this chopper stabilization, which is a continuous time version. Basically, in this here, in this circuit, we see that we have a differential sensor with single-ended output, and we have two time varying two pulse trains which are biasing these variable capacitors. So what happens is that the pulses at the input, they have a given frequency. So the DC changes of CP and CN are being modulated with that frequency. So that will be our signal, which if you look at the bottom figure to the left, you see the signal is a low frequency region. And when this is modulated, the signal will be given to go up to a given frequency, which has the frequency of FC, is the frequency of the signal at the input, and then the signal will be moved up to a higher frequency band. But all the errors which are in the system due to the amplifier and the biasings and whatever that happens here, noise, these will still remain in the low frequency region. So the signal basically is changing the capacitors, and then they are being modulated to a higher frequency by this input capacitor, and then it's being amplified and demodulated. So when the demodulating is happening, what happens is that the high frequency signal, the high frequency modulation signal is removed. So it means that our signal is being moved back to the low frequency region. And then but the noise which were still in the low frequency, or the errors, I mean, which were low in the low frequency region, is being modulated into high frequency region by FC, and FC is the frequency of this demodulator here. And normally these are the same, so the input clock frequency and the demodulator frequency is in the same, has the same value. So, and then by at the end using a low pass filter, we can remove the noise at the higher level. So again, many of these things, either by using this chopper stabilization, where you chop it in, bring it into high frequency, and at the same time using capacitors, such as in the correlated double sampling, to remove the unwanted system. So these can be combined. And then to get really high frequency, high quality signals. Again, it's a little bit difficult for me to try to give you a good overview of all the techniques and how they are implemented in detail in a 1-hour lecture. But so sometimes I feel right now when I'm talking is not being complete. But again, I'm just trying to try the best I can. So I'll give you some examples. So yeah, this is the one here, and then how it's implemented is basically, one of the implementations can be like this, where we have the switches and the capacitors and how they operate. And then basically yeah, so I have the references, which I forgot to have here, but I think if you're interested, you can contact me, or you can find many of these different, many implementations of this technique on the, for example, IEEE Explore. So it's easy to find. So here's a system which combines the two techniques, the correlated double sampling. Basically, you have clocks which have sampled the unwanted values and stored them on capacitors, and then is being subtracted from the signal in the when the timing is right, depends on how the clocks are switched on and off. And this circuit also combines, so it basically combines the correlated double sampling and also adds the chopper stabilization technique into it. So you can add many of the different techniques into the same system. So how this one works, it's kind of, you have to follow the clocks to see, for example, at Phi1, then you see that the capacitors are being biased by VRF and VRF minus. And then you can see what's happening. And then in order to charge these capacitors, you need to put their output to ground. So you charge the capacitors. So Phi1, this one is connected. At Phi2, then Phi1 opens, and then these two are grounded, and the input goes through. But at the same time that this happens, some of the unwanted biases into the circuit are being stored on the capacitor. So it's a little bit complicated clocking, but it's possible to find out. As you see, the systems becomes a little bit complicated, and this is the cost of using this kind of techniques, because you need to have clock signals which are basically non-overlapping. So how to achieve non-overlapping clocks? Then you need to basically have circuits which create these non-overlapping clocks, and these circuits will consume power, they consume area on chip, and here we have only two clocks, Phi1 and Phi2. Here we have Phi1P, Phi2, Phi1N. So it's a little bit more complicated version again, or implementation, which needs even more clocks than those. So it needs more to have the timing clocks, and the whole thing becomes more complicated. But sometimes that's the cost you have to pay for such a system. So here you see in this one here, we have 1, 2, 3, 4, 5, 6 clocks which are needed to have this kind of simple circuit work the way we want them. And then yeah, so things becomes more complicated, but again, sometimes this is what we need, because if the value of the changes are small, we don't want them to disappear in the unwanted circuits, the noise and the biases in the circuit. Then we have to implement these techniques. Yeah. So that was the techniques I showed you. These are without feedback. So it means that the output doesn't control the input signals. But there are also other techniques which are presented in literature where the output signal is being fed back to the input to control the clocks. And most of the techniques which are presented are combines many of the things that I told you. For example, the correlated double sampling and the chopper stabilization, and also they create an output which is kind of digital signal. So this one is based on delta sigma modulator technique, signal processing. So delta sigma modulators are a kind of AD converters which where the output is time varying, is pulse train, which the output is varied by over time, and the information is kind of stored in that. So normally in a delta sigma modulator, you have the output is a pulse train, and then the more ones you have, it's high values, and the more zeros you have low value at the input. So delta sigma modulators, again, is a topic that I discuss in my class before I present this technique. So this is something, is a kind of prerequisite for this the technique I'm presenting. So it's but basically the advantage here is that you have the output which also controls some of the input and the clocking. So almost feedback is always good, but again, the cost is that it becomes more complicated. And what kind of delta sigma we want to use, first order, second order, because delta sigma has many good properties that can be used in signal processing, which I don't want to go into. So for sensor systems, the signal bandwidth is rather moderate. So sometimes you need high resolution, and then high resolution, then you need delta sigma modulators, because those are kind of oscillators, no, AD converters, which have really high resolution. And one of the areas they were used was in DVD players and CD players. I think the way the information is stored on the CDs, it's because is that you want to have high resolution of the data. So yeah, so that one of the areas which it can be used. Again, there are many different topics in this 1 hour lecture. I don't think I can cover everything, but I just give you a taste, an idea what can be used in this kind of techniques, in this kind of systems. So again, there are also some cases where the sensor is floating. Here in this case, this is not the common case of sensors. Then it has its own challenges that can be dealt with, and then Again, there are different techniques for that, so I don't want to go into this, but there are really good. There's been some work on the has been presented by researchers on this topic also. So to finalize, to conclude, is that so often the sensor capacitance value is very low, especially in micro nano sensors. It's incapacitive. So in capacitive ones, they are in picofarad or less. So these often it's necessary to measure small capacitor sensor values in present of much larger parasitic capacitance values. So, and then also when you have these capacitors, then the signal is so low that it can drown basically in the other types of signals to noise. And then, so sometimes we need to shield the sensors. Yeah, and then in sensors with large signal bandwidth, because we need to do, if the signal has large bandwidth, then we need sometimes, as you saw, we need to use some high frequency signals to modulate the signal. And then if the signal has long bandwidth, then we need higher frequency, then it becomes more challenging. So again, there are some challenges. Normally, differential readout gives higher response and better control of the offsets. Is the simplest thing to do when you want to make sensor, make a differential ones. And then using other techniques such as correlated double sampling or chopper stabilization, or storing the values on capacitors in different ways, or combining these two. And these two, since they are based on switches and capacitors, they suit really well for the modern IC technologies, the MOSFETs. So yeah, that's the final. Thank you for your attention again. I tried to keep this lecture short, 1 hour, without going into the details, but I felt that this lecture wasn't, it needed more. So for you to have a good understanding of it, you need really have good background of this lecture. So it was just to give you an overview of the topic. Okay, thank you.